Hi everyone, Nicole Granucci here, and what I'm going to do is do a video on conservation of energy. So what I'm going to do is take you through both concepts and calculations. In fact, what I probably will do is just to break up this video. The first part of the video, I'll just do concepts and just kind of do that. I'll stop a video, upload this, and then do calculations. This way they're kind of separated out, so it's not this big long video. So we'll calculate the different forms of energy, we'll talk about analyzing systems, and using conservation of energy. Oops, there you go. Okay, so the objectives, so we're going to look at, basically we're going to analyze systems like I kind of talked about earlier. We're going to be able to identify work if it's done in the system, identify and calculate types of energy, look at it in a perspective of gaining, losing, or maintaining energy, and then using the conservation law equation to solve questions. So here we go. So this would be a classroom demonstration, which I'm not going to do. So, but an interesting question. Which has more energy? So there's three types of energy of a spring moving up and down, and I'm quickly looking around to see that I don't have anything like this right now to demonstrate, but you can imagine a spring, right? Actually, I can demonstrate this, so I will. Let's go ahead and do that. Good old FET. Let's see what I need. I need motion. Perfect. I love the internet. Sure. It doesn't matter. Okay. So imagine you have a spring, and let's put some mass on it, right? And then I'm just going to go ahead and let it bounce. Nope. I want it to bounce. So I guess I wanted the bounce one. Sorry. I'm learning. Here we go. Let's try this again. That's nice that there we go. Okay, so the question is, given this scenario, what kind of energy has the most amount of energy? So in other words, is there more energy in the motion of this? So notice that it has kinetic energy because it's moving up and down. Is there more energy in the spring, the fact that it gets stretched each time? Or is it from being at a height? So I'm just going to do a mental average of this, about here, from here to here. In other words, using the ground level. Is there more energy in this height? And we'd actually do a physical experiment with this, because I would actually bring in a spring and do this with you. Does this automatically do it for you? No. That's fine. That's fine. So anyway, I would measure the speed, I would measure the K constant, and I would measure this. So let's stop this so it doesn't keep going forever. And let's come back to here. And I would pull the class. And turns out, I think shut off. It turns out that of the three here, the one that has the most energy, if I were to calculate this, is going to be, well, not necessarily at rest, but more that it's at a displacement or at a height. And the answer is this one. GPE generally, not always, but generally has more energy than when it's moving or when it's stretched. That's because when you do work against energy, gravity, the factor of G already includes a factor of 10. So it generally is a very large number when you calculate it. So spoilers for later on with that. And then, again, this is about the Okemo at the skier mountain. So I love this picture because I actually have a jacket just like it, and it sort of looks like me. So I like pretend that it's me on, I don't know, some cliff in Colorado. But like I said, in advertised, I have real data from my ski trip that I did at Okemo to see which one had more energy. going through this really quick because we've done this already, but here is kinetic energy. We could calculate that with 1/2 mv squared. Gravitational potential energy is mgh, just like that. And then elastic potential energy. These are all things we talked about. This one, because it's just a little unfamiliar, is K again is the spring constant, which is just a big word of how strong your spring is. The bigger the K, the stronger your spring. And X is your stretch, how much you stretch out that string. So again, elastic potential energy has to do with position. So it comes into potential right here. So these are the actual numbers, and you can calculate these. Like, I kind of ruined it for you already. I forgot about this part. Which is fine. But if you quickly go through each of these calculations, you would find that this actually is the most. So the KE is 1/2 0.1 kilograms, as I written over there, times 0.514 meters per second squared as such. This is mgh, mgh, and then this is 1/2 K X squared. Okay, I'm going to calculate those right now. So 0.5 times 0.1 times 0.415, 0.0132 joules of kinetic energy, 0.1 times 9.81 times 0.4. This one, I'm running out of space, gives me 0.392 joules of gravitational potential energy. Oops, that's not a B. Oh, it's not a B. Let's use a P. There we go. And then this one, 0.5 times 9.32 times 0.09 squared. We have 0.0377 joules of elastic potential energy. Okay, so as I already mentioned, this has the most. Now, of course, there are cases when this is not true. If you had a tiny little height versus a big stretch and a fast motion, then obviously these would change. But I like to just do this as a quick experiment because I think people underestimate how much energy you can have just by displacing yourself against gravity, because it doesn't feel like you have any energy. I mean, even the spring feels like you have energy when you stretch it out. I have a rubber band right here. Let me just get rid of this actually so you can see my video a little better. Yeah, so if I stretch this feels energetic. If I move myself up some distance, it doesn't feel very energetic. So that's kind of the main point of that, is to show you that there is energy with height. So total mechanical energy is the sum of all the energies in the system. So written as such, total mechanical energy, TME, is kinetic plus gravitational plus elastic. I hope you know that most of the time, you're not going to have all three forms of energy. That maybe you just have one form or two, and that's okay. So let's take a look at this case. So we have a blue jay right here, and we want to find its total mechanical energy, TME. Actually, I'm going to switch this to the thicker one. I think I like that better. So it's going to be the kinetic energy. Well, you know what? I'm moving too fast here. Before I start calculating, let's read the problem. We have a blue jay. It's a pretty big blue jay, very heavy blue jay, fat blue jay. Flies at a constant altitude at 850 with a constant speed of 15 meters per second. What is the total mechanical energy of blue jay? So, of course, mass is important, as in except for the, notice that the energy has nothing to do with the mass. It has to do with the spring, which makes sense. Constant altitude. So that altitude word does refer to height. So this is a height variable. And then the speed is a velocity variable. And notice that there's no elastic energy here, and that's okay. I mean, we just ignore that term then, that whole thing's zero. So if I wanted to find the total mechanical energy of this is going to be 1/2, well, I'll just write this first, is the kinetic plus the gravitational potential, which then becomes the following equation. And notice basically I just redefined it in terms of their equations, so I get 1/2 mv, which is 15 meters per second, squared again, common thing that people mess up, 1.5 kilograms times 9.81, I ran out of room, times 850, sorry about that, like that. I screenshotted myself. Okay, so of course you could do this however you want. I'm going to do it in parts. 1/2 times 1.5 times 15 squared gives me 168.75 joules of kinetic energy. 1.5 times 9.81 times 850 gives me 507.75 joules of potential energy. And notice again that trend that I told you, the potential energy was way more than the kinetic, surprisingly. Now I'm just going to take those two numbers and add them together. 12,676.5 joules of total mechanical energy. So this bird has energy in not only flying, so moving, right, but energy in its height. It has a lot of energy. In other words, if this bird were to just suddenly drop, it would take this, all of its energy would actually go into its motion, so it would actually speed up. That's how actually conservation works, but more on that later. But the point is, we can calculate total mechanical energy just by adding the sums of the energies together. So coming back to this, okay, I just wanted to see where I was going here. So kind of the same question. What happens if I have a skier at the top of the mountain, 1160 and 25? So here's our skier question. Put on a purple hat today. I think that's what I'm going to do. Purple hat. Floof on it. Beautiful. Okay. So when I was taking my data, I used this app called Runkeeper, and Runkeeper can keep track of not only how far you've gone and how fast you've gone, but it also keeps track of elevation. So I took my phone, put it in my pocket. Here's my obscenely large phone. I put it in my pocket, and I wanted to see how fast I was going on the bottom. Actually, this was like the big thing. I was like, man, I'm a fast skier. I know that I go really fast. I must be going like 100 miles per hour. Not really. I was like, I must be going at least 60 miles per hour at the bottom of this hill. There's no way that I'm going slower at the bottom. My hat's flying off. That's why it's like that. So my energy up here, and I think the slides actually said my mass, 60, okay. So 60 kilograms. So my, and this is, I was at rest, so my initial velocity is rest up here. So my total mechanical energy in the beginning, or the initial, notice that this is my initial point. Initial. And another point is the system is this gear. And in the question, it's not super implied, but I'm going to tell you now that there is no work done. In other words, there's no friction in this fictional case. Or there's no applied force. In other words, I'm not pushing my ski poles when I do this. So my total mechanical energy initial is going to be the sum of my two types. So my kinetic energy is a boring 0 because I'm not moving, right? So you don't have to go through the motion that I'm going through right now, but I do put it there to show you that I did consider it. And then this is my potential energy. So, of course, my kinetic energy is 0 at the top. That's 60 times 9.81 times 1160. 6, 8, 2, 7, 7, 6 joules of energy. 682,776 joules of energy total at the top. Initial like that. Pretty amazing. Let's take a look at my total mechanical energy at the bottom. And you know what you could do too? You could put little F's here to signify the end point, and I's here to signify the initial point. Now, another point that I'm making kind of that I'm implying is that you can choose your final initial point. I could choose my final point in the middle, but the problem with choosing the middle point is that I have both speed and velocity. So I could solve it as long as I had both of those values. But it's so much easier when you can pick endpoints when one of them is clearly 0. Like this case, we can assume that the height's 0. So this whole term is 0. So the total mechanical energy at the bottom will be 1/2 mv final squared. Now, the moment you've been waiting for. When I got my my run keeper, it said I was 25 miles per hour. So that was not 60 miles per hour, which I wanted it to be. But I was going pretty fast. I was going about, I'm just going to erase this. A little under, which is 56 meters per second. So pretty fast. I was going fast. By the way, that's pretty fast, right? I would not want to not know how to ski at that speed. So anyway, here's the calculation. Like that, so 56 squared times 60 times 0.5. So a whopping 94,800 joules like that of the final. So a couple of things. First of all, notice that the initial does not equal the final. No initial work. So by the way, I'm just going to actually get rid of that. because it's actually not proving my point that I want to make. So ignore that comment, sorry. So notice that the initial is not equal to the final, right? The initial was 82,776 joules of energy, which is not equal to final, which was 94. Notice the initial was larger than the final. So, if you notice or think about it, if the initial is larger than the final, then energy was taken away, right? And if energy is taken away, usually the culprit of that is friction. In fact, you do want friction when you go skiing. You can't go straight down. I don't know if you know that, but you can't. If you do, you go way too fast. So here's an example of energy's not conserved. In fact, you can take the difference of these two numbers and see how much energy you lost, right? So the change of energy a lot. The change of energy and actually I did this wrong. Although this is correct, change is always the final minus the initial, and I actually did the initial minus the final. So really, the answer should be negative, right? Because I lost energy if I flip these two around. So I just want to make that correction. So negative and what we say is if there's a change of energy, that went into work done on the system. And in fact, this is the energy that went to the work done by friction because it took away energy. So a lot of energy went into the environment. In other words, the ski slope or the ground took my energy away. That's what conservation of energy really says. So as a fun exercise, what happens if all of my energy was conserved? Well, then my final, so 682,776 joules of energy, if that went to my final energy, let's see how fast I would go. So let's say that equals my final kinetic energy, which is what we found, right? The final is equal to the kinetic energy because I'm moving at the bottom. So that would be 682,776 joules is equal to 1/2 60 times v squared. This is asking the question, how fast without friction would I go? So I'm going to go ahead and solve that. 682,776 times 2 divided by 60, square root the answer. V is 150.86 meters per second. So 150, so that sounds fast. That's in meters per second. I'm going to convert this to miles per hour. You don't need to know how to do this. But that's 337.92 miles per hour. That's no friction. Imagine. That is way, 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 way too fast when you do this. Actually, I am pretty sure I did this calculation wrong, which makes me upset. So it was 25 miles per hour, and actually what I should have done is, I think it's 25 divided by 2.24. Yes, I did that wrong. I am so sorry. This should have been, I knew that was large. 11, which changes this number, but that's okay. The calculation's still the same, and you still lose a ton of energy when you do that. But this is correct because the meters per second are usually lower, so that makes sense. But anyway, the point is I'd be going about 300 miles per hour, so half the speed of sound down the ski slope if I went straight down with no friction. That would be the ski slope from hell. I would not enjoy that. I'd lost my hat. I would be going way, way, way too fast. I would not want to. I wouldn't know how to stop going that fast. I don't think I could. I think I just have to go forever. I don't know. So anyway, another way to think about and to use energy and conservation. So that's what I do here. This is the official definition of conservation of energy. No work is done in the system. The total of energy remained conserved. TME is merely transferred from one form from another, and the two forms remained unchanged. So that's just a big way to say the initial is equal to the final. Exactly like that. So we could write this mathematically as the following. The total mechanical energy initial equals the final. Or if you find the change, there shouldn't be because those numbers are the same. But if there is work, then they don't equal each other. So in physics speak, this is actually called work by non-conservative forces, but just honestly, you don't need to worry about that word. I know that's what NC means. You could just think of it as work. In other words, if there's work done on the system, then the energy does not stay the same. And just like we found, if the initial is greater than the final, then energy was removed from the system, and vice versa. If the final is greater than the initial, then energy was added. As hopefully this makes sense. And like I said, the biggest culprits is friction here, and then you have pushing or pulling here. So those are the two works that you can get. So you could honestly, you don't have to worry about, this is exactly what I said. So the total final minus the total initial. If there is work done on the system, just like I showed, you'll see this will be non-zero. But if it is conserved, then this will be 0. This is just two different ways to write the same kind of thing. I actually like to do this one because I think it makes more sense. That if I find that there is a difference, and if it's positive, then that's work added, and if it's negative, then that's work subtracted. I find that this one here, the second one, is actually could be confusing. I like to think of it in terms of this. Also, when it comes to adding energy, it adds to the velocity of the person or takes away from the velocity. We can't change the height. In other words, if we lose energy, we're not going to lose our height because that is actually maintained by the surface. So what happens is the energy has to go somewhere, and it does go into our motion. So here is just an example of work. In this case, no work is done on the system. And we see that the total mechanical energy is super boring right here because all you can see is that it stays the same. But more importantly, that if you added the kinetic and the potential at any one point, it would equal this. So that's total mechanical energies, adding these features like that. So these are called bar graphs, and it's a great way to think and model in terms of conservation of energy like this. So I'll be doing some more of these coming up. Another way to think about conservation of energy or the total mechanical energy is through this diagram. Now what I'm saying in this diagram is if the total, so you have to add them up, it's always going to be the same number. Major hint here, I could put an exam question on this, leaving some of these blank, and you have to figure it out. The trend is figure out the total energy, and the total must remain the same. So if I added the kinetic and the potential here, you would find that'd be 50,000. The kinetic and the potential is 50,000. But notice we're higher than halfway, which is why the potential is higher than the kinetic. If you look at here, if you add these up, it's also 50,000. But notice the potential is way lower because you are at a lower height. And notice that the kinetic is larger because you had time to move down the slope. Hopefully these values make sense. And vice versa. Since we're at the same height, notice the dotted line, we can assume that they have the same energies at that point. And then this, the bottom, is a mirror of the top. The top you started at rest and you have all height. At the bottom you have no height and you're moving. So the main goal is that conservation of energy means that this total does not change. Notice at no point does this change. We're assuming no friction or any pushing in this case, that this just happened naturally. Here's when you have work. I want you to watch this a couple times. And in fact, you can actually see this as two parts. First of all, energy is conserved before it hits the box. Notice that. But once it does hit the box, the kinetic energy goes into work done by friction. Notice that the work is negative, right? So the work is negative, which means it's taking away energy. And in fact, every time you add the kinetic and the work, you'll notice that it basically cancels out, right? So notice that at this point, all of the kinetic goes into work. Now, the energy itself is conserved in that it's the same, but it no longer goes back into the system, it goes into the environment. That's what work does. It takes energy and puts it into the environment. Or the vice versa, the environment puts energy into the system. So this is like the bridge between the system and the environment. And just to be repetitive, notice that in the beginning there is no work. So notice that this whole thing is blank. But only work is done when it hit this block right here. And then we modeled it like that. So that's it, just talking about it. Okay, so I just wanted to see. Okay, very good. Okay, so there's a whole worksheet on this, and I highly recommend you go through it because I'm going to put an exam question on this exact kind of setup. So let me, actually, I think I will stop the video at this point, and then I'll start the next video talking about all this. So just in conclusion, I'll actually come to here, conservation of energy. So when we talk about conservation of energy, it's important to identify the types of energy in the system. Generally, they're kinetic and potential, or if there's work done in the system. If there's no work, then the total energy before and after are the same. If there is work, they're not the same. This is what we talk about in terms of conservation of energy. In the next video, I'll talk about how to look at those questions and how to analyze the types of energy and the work done in the system.